So good afternoon, everyone. In the previous class, we have discussed the concepts of electric potential and capacitance. I think we have did the concept regarding parallel and series combination of capacitors. Based on those formulas, we have did two numericals. Finally, then I think we have started the concept of electric potential. We have derived the formula for electric potential due to point charge. So let us move on to the last important topic from this electric potential and capacitance, that is potential energy potential energy of dipole in a uniform electric field. In a uniform electric field. See here, half of this concept we have already discussed in electric charges and field. That is nothing but whenever we are placing an electric dipole in uniform electric field, what was happening? The net force on the dipole was becoming zero and the dipole has started to oscillate. So what is the torque acting on that electric dipole was given by the formula tau is equals to P sin theta. So by using that concept itself, we will be obtaining the potential energy of an electric dipole placed in a uniform electric field. So let me consider a uniform electric field. I said that uniform electric field lines will be parallel to each other. So let me draw this uniform electric field. So here we are having uniform electric field. In this uniform electric field, what we did, we have placed an electric dipole. In this uniform electric field, what we did, we have placed an electric dipole. Here I have considered positive charge and here I have considered the negative charge. The force acting on positive charge was F is equals to plus QE and the force acting on negative charge was F is equals to minus QE. And what was the length of the electric dipole? It was 2a. Further, what we did, we have considered a perpendicular line here. This angle was theta and this component was 2L and this component was 2L cos theta. These are the things which we have already discussed in electric charges and field. Now we are going to determine the potential energy of this electric dipole whenever it is placed in uniform electric field. Now see here, what was the formula for torque we got? We came to know that whenever an electric dipole is placed in uniform electric field, the net force acting on dipole was how much? It was 0. Whenever the net force acting on dipole was 0, we said that torque will be developed. And what was the formula for torque? It was force into perpendicular distance. Force into perpendicular distance. I said that we can consider any one of the force. Either you can consider plus QE or you can consider minus QE. I am considering plus QE. And what is the perpendicular distance? This is the perpendicular distance. What is that? 2L sin theta. 2L sin theta. So from here we got one formula for torque. Tau is equals to P E sin theta. This was the final answer. We got the torque on an electric dipole placed in uniform electric field. This was the formula we got. Now see here. Now we are going to continue this thing. What we'll be assuming here? We'll be assuming that let us make the dipole to rotate through small angle d theta. Let dipole is rotated through a small angle d theta. Then the work done is given as, then the work done will be given as, see here, dw, small amount of work done, because we have rotated the dipole through a small angle d theta. Then the work done will be given as dw is equals to torque into d theta. So this is small amount of work done or total work done. This is very small amount of work done. In order to get total work done, what we are supposed to do? We are supposed to integrate. So what this equation will become? W is equals to integral dw, that is equals to, what is the value of dw? Tau into d theta. So what is the value of tau? Torque tau is Pe sin theta into d theta. Let us assume that this angle is, there is small amount of change in angle. Now let us assume that the angle is changing from theta naught to theta, theta naught to theta. So P is constant. What will be the integration of sin theta? Integration of sin theta will become minus cos theta. So what this will become? This will become Pe minus cos theta, and theta is changing from where to where? Theta naught to some theta. You can take theta 1 to theta 2 or theta naught to theta, your wish. So this will become what? This will become minus Pe of cos theta minus cos theta naught. So this is the work done in rotating an electric dipole from position theta naught to theta in a uniform electric field. Whenever we are placing an electric dipole in a uniform electric field, then if I am rotating the dipole from some angle theta naught to theta, then how much amount of work I am supposed to do is, this is the amount of work I am supposed to do. Here we'll be considering one condition, small condition. Let theta naught is equals to 90 degree. Let us assume that the theta naught is equals to 90 degree. Then what will be the work formula? Will become whatever work we will be doing, that will be stored in the form of potential energy. Whatever work we will be doing, that will be stored in the form of which energy? Potential energy. So this formula will become minus Pe. What is the value of theta naught? Theta naught ki value is 90 degree. So what is the value of cos 90 degree? Cos 90 degree will become 0. So what will be our final answer? U is equals to minus Pe cos theta. So this is the final answer expression for potential energy of an electric dipole placed in a uniform electric field. So by this, we finish all the important concepts from electric potential and capacitance. So please carefully go through this, all the 6 questions. If you are done with the 6 questions, definitely you will be able to answer one SAQ in your annual examination. Now let us move on to the next topic, that is moving charges and magnetism. So what is our next topic? It is moving charges and magnetism. Now see here, before entering into the concepts, let us discuss some few important points regarding how magnetic field is generated and how we represent the magnetic field. See here, there was a scientist whose name was Ørsted. What he came to know is that wherever there is a wire, assume that this is a wire, through this wire a current is flowing, small amount through this wire, what is flowing? A current is flowing. Then he came to know that whenever some amount of current is flowing through a wire, around that wire some magnetic field will be created. This was the experiment done by Ørsted. He said that whenever some amount of current is flowing through a wire, around that wire what will be created? Magnetic field will be created. Now see here. So for representation, if the magnetic field is going inside, we'll be using the symbol cross. What does this cross symbol means? It represents inside. Magnetic field is going inside. If the magnetic field is coming outside, we'll be using something like this, a dot. This is used for what? Magnetic field is coming outside. Outside. It is just like an arrow. If you see the arrow, here we'll be having pointed region. At back side of the arrow, we'll be having what? Cross mark. If the arrow is going inside, which thing we'll be able to see? We'll be able to see the cross mark. So whenever the magnetic field is inside, I'll be considering the cross mark. If the arrow is coming outside, which point we'll be able to see? We'll be able to see the pointed region. So it represents the magnetic field is coming outside. Please do remember this terminology so that while solving the problems as well as while discussing the concept, it will be very much easy. See here. Next important thing. So Oersted said that whenever there is current flowing through a wire, around that wire, what will be created? Magnetic field will be created. But what is the amount of magnetic field that will be created was given by two scientists. We don't know the magnitude, how much amount of magnetic field is being created due to the current flowing in the wire. So there were two scientists named Biot, Savard. These two scientists have given the amount of magnetic field created due to a current carrying wire. This is known as Biot-Savart law. Biot-Savart law. Now carefully see this. Let us consider a current carrying wire. Let us assume this is a conductor. Through this conductor, some current is flowing. Some I amount of current is flowing through this conductor. Now, due to this wire, some magnetic field will be created in this surrounding region. Who said this? Oersted said that. But how much amount of magnetic field is being created? The magnitude was given by Biot-Savart law. See here, let us assume one particular point P. At this particular point P, we want to determine the amount of magnetic field created. For that, what we'll be doing? We'll be considering a small current element or length element here. I've considered a small length element. I'm representing it with DL. I'm representing it with what? DL. Because some amount of current is also flowing, I'm calling this entire term. What is that? IDL. Actually, there is a huge explanation regarding this because length is a scalar quantity, but the length element will become a vector quantity. So all that are other things. But I will be calling this term as what? Current element. This is called as what? Current element. Now see here, I want to determine the magnetic field. See here, I have taken only small element. Due to this small element, only small amount of magnetic field will be generated here. So I want to determine the magnetic field generated at this particular point P due to this small element IDL. So let me draw one position vector. This is R, and the angle between current element and this position vector is theta. Now, what was the explanation given by Biot-Savart law by looking at this statement, by looking at this arrangement? Biot-Savart law said that magnetic field induction produced at point P is directly proportional to current element. How, sir? See here, initially some 1 ampere of current is flowing. Due to that 1 ampere of current, some magnetic field will be generated. Assume that I have increased the amount of current. If I am increasing the amount of current from 1 ampere to 5 amperes, definitely the amount of magnetic field created at this particular point increases. Instead of 5 amperes, if I am increasing the amount of current to 10 amperes, the amount of magnetic field at this particular point will be increased. So he said that amount of magnetic field created at this particular point P is directly proportional to the current element IDL. The current element. See here. Assume that I have taken only this small amount of length element. What is that? From here to here, small amount of length element. So only this few number of electrons will be flowing through this region. So due to that few number of electrons, what will happen? Magnetic field will be created. Assume that I have increased the length element from here. Instead, I did this length element from this particular position to this particular position. If I increase the length element, the number of electrons flowing through this length element will also increase. If the number of electrons flowing through this length element is increasing, definitely the amount of magnetic field generated here or created here will also increase. So that is the reason we have written amount of magnetic field induction created at this particular point P is directly proportional to what? This is called as current element. Current element. Next thing, what is the next thing they have observed? They observed that the amount of magnetic field created at one particular point is inversely proportional to square of the distance, inversely proportional to square of the distance between current element and one particular point P. Definitely assume that initially due to this wire, some magnetic field is being created here. I am writing that magnetic field as B1. Due to the same wire, some magnetic field is created at this particular position B2. This is the distance R1. This is distance R2. Again, due to the same wire and same current flowing through that wire, at this particular position, the magnetic field is created B3 and this distance is R3. So by looking at this diagram, you can say that distance R3 is greater than R2 and distance R2 is greater than R1. But if I ask you a question, in which region, at which point the magnetic field will be more? So what you will be telling? The magnetic field at B1 will be greater than B2. The magnetic field at B2 will be greater than B3. So as the distance is increasing, the magnetic field generated or magnetic field developed at one particular point is decreasing. So this also obeys inverse square law. So this is what? Amount of magnetic field induction at one particular point P is inversely proportional to square of the distance between the point and current element, Okay, this was the second observation made by Biot and Savart. And what was the third observation made by them? They said that magnetic field induction generated at one particular point P is directly proportional to sine of angle between length element and position vector. And what? Position vector. So these were the three observations made by whom? Biot and Savart law. And they finally have given one formula for us. What is that formula? Means here combine all these things. Magnetic field generated at one particular point P is directly proportional to what? I dl sine theta divided by R square. I dl sine theta divided by R square. If I remove this proportional symbol, what I am supposed to include? I am supposed to include a constant. And that constant is given as dB is equals to mu naught divided by 4 pi I dl sine theta divided by R square. So this is the final expression for Biot-Savart law. Please do remember this expression. Based on this expression, we'll be doing one application. So this is our final expression. So let us write down the numerical value of mu naught by 4 pi. First of all, let us write down the unit for mu naught by 4 pi. This mu naught by 4 pi can be written as, how I can write? dB into R square divided by I into dl. So what will be the unit of magnetic field? It will be Tesla. And unit of R square will become meter square. And unit of I will become ampere. And unit of length element dl will become meter. So this meter and square will get cancelled. So what will be the unit for mu naught by 4 pi? It will become Tesla ampere meter inverse. Tesla ampere meter inverse. And its numerical value is equals to 10 power minus 7. This is the unit. I hope you understood this thing. Oersted said that whenever some current is flowing through a wire, due to that flowing of current through a wire, what will be generated? A magnetic field will be created around that wire. And how much amount, what is the magnitude of magnetic field created? That was given, explained by two scientists. One scientist name was Biot and other scientist name was Savart. So we came to know about this law that is called as Biot-Savart law. According to them, the magnetic field created or magnetic field induction generated at one particular point P is directly proportional to this current element and inversely proportional to square of the distance between them. As the distance is increasing, what is happening to the magnetic field generated? It is decreasing. Finally, they have given one more term that is called as sine theta. That is nothing but the angle between this length element and position vector R. So finally, we came to one conclusion. What is that? Small amount of magnetic field created due to this small length element is given as what? dB is equals to mu naught by 4 pi. I dl sin theta by r square. See here, in order to get entire magnetic field created due to the entire wire, total magnetic field created due to the entire wire, what we are supposed to do? We are supposed to integrate this magnetic field dV. After that, we'll be getting the final answer. Let us see one of the important application for this Biot-Savart law. See here. Application of what? Biot-Savart law. Application of Biot-Savart law. One important application is there which will be asked in your examination. What is that application? Magnetic field induction. Magnetic field induction at the center of a current carrying circular wire. So let us see this important application of Biot-Savart law. What is that application? Magnetic field induction at the center of a current carrying circular wire. Carefully see this. What is our Biot-Savart law? Our Biot-Savart law formula is what? dB is equals to mu naught divided by 4 pi I dl sin theta divided by r square. This is the formula for what? Biot-Savart law. By using this formula, we'll be solving this above problem. So here let us consider a circular current carrying wire. Current carrying circular wire. So let me consider one current carrying circular wire. So this is current carrying circular wire. Now see here. Current is flowing in some anti-clockwise direction, something like this. The current is flowing here in anti-clockwise direction. Now, we know that by applying right hand thumb rule, we can determine the direction of magnetic field, where the magnetic field is created. See here, curling of finger represents the direction of current. Curling of finger represents the direction of current, and thumb represents the direction of magnetic field. See here, the current is flowing in anti-clockwise direction. Current is flowing in which direction? Anti-clockwise direction. My thumb is representing outside. So what will be the direction of magnetic field at the center? It will be outside. I said that in order to represent the magnetic field inside, which symbol we'll be using? We'll be using cross symbol. This is nothing but magnetic field is inside. In order to represent the magnetic field outside, which symbol we'll be using? We'll be using a dot. This is the magnetic field outside. It represents the magnetic field is coming outside. So see here, curling of finger represents the direction of electric current, and thumb represents the direction of magnetic field. So this will be magnetic field will be outside, and it is represented by which symbol? Dot symbol. It is represented by which symbol? Dot symbol. So now we are supposed to determine the magnetic field at this particular center of the circular carrying wire, circular current carrying wire, due to a small length element, dl. I am considering a small length element dl here, and this is the position vector r. Now, what is the angle between position vector r and dl? The angle between them is how much? 90 degree. Let us determine the total magnetic field due to this current carrying circular wire at the center of that coil. Now everyone see here. Here theta is equals to how much? Theta is equals to 90 degrees. That is nothing but dl is perpendicular to what? R. dl is perpendicular to R. So let us determine the total magnetic field. It is given as B is equals to total magnetic field. B is equals to integral dB. Integration of dB will, this is dB is what? Small amount of magnetic field. In order to get total magnetic field, what I am supposed to do? I am supposed to integrate that thing. So this will become integration mu naught by 4 pi into I dl sine theta divided by r square. Let me consider the value of theta as what? 90 degree. So I'm substituting that value here itself. So what is that? Sine 90 degree. Now carefully see here. Mu naught by 4 pi is constant or variable? Mu naught by 4 pi is constant. Current flowing through this wire is constant or it is changing? Current flowing through the wire is also constant. Whether the radius of circular coil will change or remain constant, radius of that circular coil is also remaining constant. So what is the only thing which we can change? We can only change the small length element. I can increase the length of this length element. I can decrease the length of this length element. So remaining thing are what? Constant. So I can take constants outside. So what will be the final answer? See here. B is equals to mu naught by 4 pi is constant. Let us take that outside. B is equals to mu naught by 4 pi into current flowing through the wire is also constant. So let me take that I also outside. And r square radius of this circular coil is also constant. So I can take r square outside. So what is the value of sine 90 degree? We know that sine 90 degree. What is the value of sine 90 degree? Sine 90 degree is equals to what? 1. So we'll be left with only integral dl. Integral dl. So what will be our final answer? B is equals to mu naught by 4 pi into I divided by r square into, let us assume the length of the wire was initially L. Next, what we did, we have made that length of the wire into a circular coil. So this will become what? L. So here length of the wire is how much? L is equals to what? Circumference of circle. How much? 2 pi r. So this will become what? This will become B is equals to mu naught divided by 4 pi into I divided by r square. What is the circumference of the circle? It will be 2 pi r. So this will become what? 2 pi r. So from here pi get cancelled, square and r get cancelled, 2 one sign, 2 2s. So net magnetic field. This is the final expression for magnetic field at the center of a current carrying circular wire. What is that equation I am getting? Mu naught I divided by 2 into r. 2 into r. So this is the final expression for magnetic field induction at the center of current carrying circular wire. What is that? Using which law? Using Biot-Savart law. So what is that? B center magnetic field at the magnetic field induction at the center of current carrying circular wire is given as what? Mu naught I divided by 2r. So this is one of the most important application for Biot-Savart law, which may be asked in your annual examination. I hope you understood this concept. First of all, what I did, I have taken the formula for Biot-Savart law. Then what I have did, I have drawn the symbol for current carrying circular wire, and using the right hand thumb rule, I was able to determine the direction of magnetic field. See here, curling of finger represents the direction of electric current and thumb represents the direction of magnetic field. So magnetic field is coming outside. That is the reason I have represented it with which symbol? Dot symbol. Next, what I did, I have considered a small length element dl. Due to the small length element dl, I want to determine the magnetic field generated at the center of the circular current carrying coil. So this is the final expression we got. I hope you understood this expression. Let us move on to the next topic. So our next topic is Ampere's law. So what is the next topic? Ampere's law. So what is this Ampere's law? First of all, I will be writing the formula. Based on that formula, we are going to write down the statement for Ampere's law. What is the formula for Ampere's law? It is given as closed integral d bar dot dl bar is equals to mu naught I net is equals to what? Mu naught into I net. This is the formula for what? Ampere's law. Based on this formula, we will be writing the statement for Ampere's law. See here. This term is called as See here, integral is there. Which element is there? Length element is there. This is called as line integral. Line integral of what? Line integral of which field? Which physical quantity? Magnetic field. Line integral of magnetic field. Magnetic field. So what is the definition for this? What is the statement of Ampere's law? The line integral of magnetic field. What is the name of this symbol? The symbol represents is equals to. Is equals to. I hope you remember the Gauss law. In the Gauss law also we did the same thing. We have written the formula. Based on that formula, what we did, we were able to define the statement, or we were able to write down the statement. The same thing we are going to do. What is this? This is the line integral of which physical quantity? Magnetic field. And this is the symbol for is equals to. And is equals to what? Mu naught times. What is it? This is mu naught times I net represents net current. I net represents what? Net current enclosed. Net current what? Enclosed. So this is the statement for Ampere's law. What is the statement? Line integral of magnetic field is equals to mu naught times the net current enclosed in a circular loop. See here, it is applicable for which type of surfaces? Closed surfaces. Applicable for which type of surfaces? Closed surfaces. So I can write down the statement for Ampere's law. What will be the statement for Ampere's law? The line integral of which physical quantity? Of magnetic field. Of magnetic field. Of magnetic field around a closed surface. Around a closed surface is equals to mu naught times, is equals to what? Mu naught times the net current enclosed in the surface. Enclosed in the surface. Enclosed in the surface. So this is the statement for which law? Ampere's law. What does this Ampere's law state? The line integral of magnetic field around a closed surface is equals to what? Mu naught times the net current enclosed in the surface. Let me consider one example. Let us consider one closed surface, something like this. Here I am having a closed surface. Now, through this closed surface, some amount of current is flowing. So here, some amount of current is flowing. One current is going inside. One current I1 is going inside. Again, it is coming outside from this particular region. Next, there is another current wire through which current is flowing. Let me consider that current is flowing here from this region, and it is coming outside from this particular point. So it is coming outside from this particular point. There is one more current which is coming outside from this particular region. There is one current which is coming outside from this particular region. So here, this current is coming inside, and these are the currents going outside. These are the current going outside. So see here, I said that whenever magnetic field is going inside, I said that we'll be representing with cross symbol, and whenever the magnetic field is coming outside, we'll be representing it with dot symbol. Now the same thing we are going to do with that current wires. When the electric current is going inside, we'll be representing it with cross symbol. When the electric current is coming outside through a wire, we'll be representing that with a dot symbol. So let us represent those things. let me erase this thing. No need of this thing. Just I will be drawing a simple diagram. No need of this thing. Let me draw a simple diagram. I can explain this like this also, but let us draw a simple diagram. So here, let us consider a closed loop. Here, few currents are going inside. Let me take this dot. What does dot symbol represent? Whether the current is going inside or coming outside. It represents the current is coming outside. I am taking this as current I1. There is another wire through which current is going inside. I am taking that current as I2. There is another wire through which current is coming outside. I will be representing that with cross symbol. Let me take that current as I3. I am having one more wire which is coming through which current is coming outside. Sorry, current is going inside. I will be writing this current as what? I4. So see here, we should consider the current only inside the closed surface. If there is one more wire, here I am having a current I1, I5, I1, I2, I3, I4, I5. Here I am having one more current. Here it is I6. Should I consider I5 and I6? No, I should consider only I1, I2, I3, I4, because this law is applicable for what? Closed surfaces only. It is applicable for what? Closed surfaces only. So see here, what will be the net current? I can write I net. I can write the net current. I net is equals to I1 plus I2 minus I3 minus I4. Here I have considered that the current which is coming outside, I have taken that one as positive, and the current which is going inside, I have taken as negative. In some books, you will be finding that the current which is going inside as positive and the current which is coming outside as negative. Your wish, you can follow anything. So the net current through this closed surface is how much? I net is equals to I1 plus I2 minus I3 minus I4. So what will be our final formula? Our final formula will become, for this particular surface, closed integral b bar dot dl bar is equals to mu naught times I net. So if I substitute this value, what this will become? Closed integral b bar dot dl bar is equals to mu naught of, what is the net current value I got? I1 plus I2 minus I3 minus I4. So this is the statement and explanation of which law? Ampere's law. So what is the statement for Ampere's law? The line integral of magnetic field around a closed surface is equals to what? Mu naught times the net current flowing through this closed surface. So what I have did, I have considered a closed surface and I have taken four currents. I1 and I2 are the currents which are coming outside, which I have considered to be positive, and I3 and I4 are the currents which are going inside, which I have considered to be negative. So what will be my net current? My net current will become I1 plus I2 minus I3 minus I4. So finally, I have substituted the value of I net here. I got this expression. What is that? Integral b bar dot dl bar is equals to mu naught of I1 plus I2 minus I3 minus I4. Let us see one application for this Ampere's law. Let us see the application of this Ampere's law. Application. Application of Ampere's law. This application is very important for your main examination, annual examination. That is, magnetic field due to a magnetic field due to a straight current carrying conductor. Magnetic field due to a straight current carrying conductor. So this is, by using Ampere's law, we are going to obtain an expression for magnetic field due to a straight current carrying conductor. So let us consider